Good morning and welcome to this next lecture on sound and structural vibration. We were modeling a radiating panel using monopoles and we are giving suggestions for further refinements. Okay. If a single phase cell is inadequate, we could divide it into subcells, and further, because the mode itself has varying velocity over the panel, we could allot appropriate amplitudes to the subcells. So these two aspects give huge improvement in numerics. Okay. Now let's start looking at some derivation. So we have pressure from a monopole, This I expect you to know from acoustics. That's okay. The P and some R, okay, is J omega rho or rho 0, as I've said before. The volume velocity e to the power of minus j k r over twice pi r, not 4, because the monopole in a baffle placed on a wall by itself is a doubling of pressure. Okay. Now we have to deal with now distances. Okay. Source distance to receiver distance. The source is the cell and monopole, and receiver is the receiver point. So we have to locate, although it's a certain volume velocity, I have to locate it in some place. So I locate it at the corner. I'm going to locate this at the corner. Okay. So the whole dimension is placed at the corner, and it will not cause too much of an error because we are going to look at the distance from the source to the receiver, which is very far. It's a far field. Okay. So from that distance, the distance spatial extent of the monopole is largely irrelevant. So I will find a convenient point, which is the left lower corner, to place the monopole. Okay. So now if we are going to still look at M1 is 4 and N1 equal to 7, we are looking at that. Let me put my coordinate system. So I have a panel here, 1, 2, 3, 4, 5, 6, 7. Okay. And in this direction, let's see. Is 4 7 1 2 3 4 5 6 7 4 7. Okay. So let us say I am looking at a receiver point somewhere here, far away of course. This is my x, that is my y. Okay. And then I have, this is a, this is 2a, and somewhere I have ma. Okay. And this is my z axis. This is my z axis. Okay. Then let's call this my let us call this my r. Okay, it's some x comma y comma z. Okay, and I am looking at some location. So this cell is located here. So let us see that distance. This distance is my R. Transmitter to receiver, that distance is R. Okay, so in this direction we have 1b, 2b and nb. Okay, so now what is R? We will need R, right? What is R? Okay, so R, let's say, or R square is x minus ma whole squared plus y minus nb whole squared plus z squared. Okay, so now we need an index. We need an index for the cell. Okay, which also represents the distance, right? ma will be the x distance, nb will be the y distance. So the first cell location is at the left hand corner, so it's right here. So my m and n shall begin from 0. So m will go from 0 to m1 minus 1 and n will go from 0 to n1 minus 1. Okay, ma and na are the distances of that monopole from the origin. Okay, so this happens to be my r square. So let us expand it. R square is equal to x square minus twice m a x plus m square a square plus y square minus twice nby plus n square b square plus z square. And what is this number here? X square plus y square. This is the distance of the receiver from the origin. It's r square. Okay, so we write this as r square minus twice m a x minus twice n b y plus m square a square plus n square b square. Okay, which is equal to r squared, I take it out, 1 minus twice m a x over r square twice n b y over r square plus m a by r whole square plus n b by r whole square. Okay, now what I am going to say is that m a by r, the distance from the origin of the cell over distance from the origin of the receiver is a very small quantity, epsilon. Okay, so then these terms carry epsilon, these terms carry epsilon, these terms carry epsilon squared. So these are much smaller and we'll drop them. We'll drop these terms. Okay, so I get now this is r squared. Okay, I take the square root, we get capital R is equal to R into 1 minus max over R square minus nby over R square. Okay, where what have I done? I have done root over 1 minus 2 epsilon is equal to 1 minus epsilon. I have done that binomial expansion. I have removed the square root. That's how this. I drop these terms, then I am left with R square, took a square root. These are small terms, twice epsilon terms, so I made them 1 minus epsilon. I have reached this point. Okay, so now the pressure is a sum. Now the pressure at that point R, let's say, is a sum. Okay, so we are keeping the time term out by now, you know, right? So summation m equal to 0 to m1 minus 1 summation n equal to 0 to n1 minus 1 j omega rho q by twice pi r, okay, e to the power minus j k r minus max over r minus nby over r. Okay, so that's the pressure summed over all the monopoles. Now we get pressure at the receiver point given by j omega rho 0 q. I forget what I did. So I took rho, so I'll take rho here, sorry. Rho q by twice pi r, it's common. Further, e to the power of minus j k r is common outside. Then this double sum, okay, 0 to m1 minus 1, 0 to n1 minus 1, e to the power of plus j k max over r plus nby over r. So we have to compute the intensity and we have to integrate over the hemisphere. Somewhere some integration will be there, which is simple enough, but we have to compute intensity, far field intensity, which is magnitude PR square over twice rho c. Okay, so first we need magnitude of pressure. So that does what? The j goes away, exponent goes away. So I have omega rho q by twice pi r. Then the amplitude of this term, the amplitude of double sum, I will break it up inside cosine of k max over r plus nby over r plus j sine k max by r plus nby by r. So this is the real term, this is the imaginary term, okay, and we are trying to get the magnitude of this thing. So now magnitude of this thing is equal to omega rho q by twice pi r. Okay, so this is square root of double sum cos whole squared plus double sum sine whole squared. Okay, so real squared plus imaginary squared square root, that is the amplitude. Okay, so then p of r whole squared is omega square rho square q square by 4 pi square r square into double sum cosine whole squared plus double sum sine whole squared divide by, okay, so divide by twice rho c. So I'll divide this by twice rho c. That is my intensity. Okay, and we have to multiply by r sine theta d phi r d theta in spherical coordinates. Okay, where theta is the elevation angle measured this way and phi is the azimuthal angle measured this way. Okay, r sine theta d phi r d theta. Okay, now you integrate. Now you integrate this. Now you integrate this. Integrate p r squared by twice rho c, you integrate. Okay, with what? Theta limits 0 to pi by 2, phi limits 0 to twice pi. Okay, so r sine theta d phi r d theta, you integrate, and it is relatively easily integrable. Okay, once you integrate that, this power, let me give it this symbol here, the power is given by 32 k square, okay, a b by pi to the power 5 m1 n1. Okay, into m1 n1 first term plus summation over m equal to 1 to m1 minus 1 twice into minus 1 to the power m n1 into m1 minus m sine mka by mka plus summation n is equal to 1 to n1 minus 1 twice minus 1 to the power n m1 n1 minus n sine nkb by nkb. So we'll denote the terms later. Okay, so summation m equal to 1 to m1 minus 1 n equal to 1 to n1 minus 1 4 minus 1 to the power m plus n m1 minus m into n1 minus n sine kr over kr. So there are 4 terms. This is the second term, this is the third term, this is the fourth term. There are 4 terms and this is general. Okay, I am demonstrating with respect to m14, n17, but this is a general expression. Okay, so now what are each of these terms? So what are each of these terms? Each of the terms, what do they mean? Physical. So remember m1, m1, n1 and this term in front. Okay, so let us see. So we have the terms, let us call it terms. The first term given by 32k square AB by pi to the power 5 m1 n1 is power from a single cell. On a baffle, single phase cell. Okay, single phase cell on a baffle with no other source, no other source, no other source. Okay, so inside we have what? m1 n1. So this multiplied by m1 n1 is the power from all the monopoles. There are m1 n1 phase cells, so for all the phase cells, that's the first term. Okay, so this is the first term. Okay, so we are now demonstrating, for m1 is equal to 4, n1 is equal to 7. I am making it specific now. Okay, so the second term, how does it look like? Term 2, how does it look like? It looks like summation m goes from 1 to m1 minus 1, so 3. Okay, there is a 2 in front with a minus 1 to the power m into n1, which is 7, into m1 minus m, so 4 minus m. Further, sine mka by mka. I need the schematic for this, so let me go here, let me say here. So again, let's see, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Very good. Okay, so I have 4 by 7. Okay, so this is y direction, this is x direction. Okay, m1 n1. Okay, so now let us see, if I open this term out, okay, I get for m equal to 1, I get twice into minus 1 to the power 1, 7, 4 minus 1, 3, and sine Ka by Ka. Okay, this is distance is A, this short distance is A, this short distance is B. Okay, so I get a negative value, I get 7 of these represent 7 rows. Okay, and I get 3 of something. What is 3 of something? I get 3 interactions of cells, of neighboring cells, of immediate neighboring cells. Across the node line. So I get an interaction of this cell with that cell, immediate neighbor, that's 1. I get an interaction of this with this 2, this with this 3, that's the 3. And this is a plus, suppose, then this is a minus, and this is a plus, this is a minus, so there is a phase change of a -1 across the cell, that's this phase change. And I get 7 of these because there are 7 rows, 1, 2, 3, 4, 5, 6, 7 rows, and I get a 2 because there are 2 cells involved. Interaction of this with this, interaction of this with this, 2 cells involved. That's the meaning of the first term. Okay, for m equal to 1. So when m equal to 2, now within this summation we are looking at the term 2. So when m equal to 2, I get twice minus 1 whole squared, so positive now, again 7. Okay, but this time 4 minus 2, which is 2, into sine 2 Ka by 2 Ka. So in a sense this is actually the actual interaction term. Okay, so you can see that as m increases, m was 1, so Ka over Ka, this Ka diminishes, reduces, because sine has a peak value of 1. So now here it is 2 Ka. Okay, so the distance is now more, so interaction effect is less. So let's see the meaning of these terms. So now the negative is gone, this positive. There are 7 of these, again to describe the rows, and there are 2 of this. What are the 2 of this? The interaction of cells with a gap of one cell, So this cell interacts with that cell and this cell interacts with that cell. Okay, there are 2 such interactions in a row. There are 7 rows. The interaction is without a sign change because this is positive and that is positive, or this is negative and that is negative. Okay, and 2 because there are 2 cells, this interaction with this and this interaction with this, there are 2 cells, so that's the term. Okay, and again as I said, this describes the interaction effect. Okay, so as the distance, this distance increases, now it's 2 Ka, the effect is reduced. Okay, so now the next term we have for m equal to 3, which is the last term. Okay, for the third m equal to 3 within the same term 2, is we get again 2, this time again minus 1 to the power 3, the 7, and then 4 minus 3, which is 1, and sine 3ka over 3k. Okay, so this is interaction of cells with a gap of 2 cells. Okay, I am running out of time. We will close here, continue in the next class.